welcome. Today we are going to start a new topic, which is digital electronic voltmeter. Before we dive into that, let's recall that previously we have studied how to measure frequency using a counter. Okay. Now, can we measure something else using a counter, say like mass or weight of something with a counter? Okay. So, say we have a balance, okay, like this. So, this is a balance which two plates, okay, and it has an indicator. So, this is like a regular balance, and where we put the unknown weight on one plate. Okay. So, this is unknown weight, and on the other pan we generally put a known weight, and then the moment when this indicator is exactly at the middle, then that means the unknown weight is same as the known weight. That is how we measure weight using a balance. Now, I am going to have a slightly different scheme. So, what I will do here, I will put a beaker. Okay. So, this is a beaker, empty beaker. Okay. So, you can think this is a massless beaker. Beaker means it's basically a container. Okay. And here I will take a tap of water. Okay, like this. And the speciality about this tap is that the water flow rate is constant and known to me. Okay. So, water flow rate is constant, and say this is equal to m gram per second. So, the moment you turn this tap on, it will start giving water at this rate, and you can stop it, but you cannot change the flow rate. You can only turn it on or off, and the flow rate will always be constant. Now, together with this, I also have a stopwatch. Okay. So, let this be a stopwatch. Now, the idea is I have to measure the weight of this unknown thing. How do I do it using this stopwatch and this scheme? It is simple. So, I will start with empty container. Start with the empty container or beaker, and then start the tap and start the stopwatch together. And the moment when so initially it was empty, so it was heavier, okay, and as water flows here, this will go heavier and heavier, and at some moment the weight of these two will be equal, and then the pointer will be exactly at the 0 position. So, at that moment when the pointer is crossing the 0 position, I will stop the stopwatch. Okay. So stop the watch at the moment when the weight of the water is same as the weight of the same as the unknown weight. Okay. Now if the time required for this process to happen if is equal to time required, if this is equal to say t, then we can easily say, okay, then the weight of this unknown weight called wx, okay, this must be same as the total amount of water that has been stored in time t, which is same as t multiplied by m. Okay. So then wx must be equal to t multiplied by m gram. That's as simple as that. Okay. Now we will use this same idea for measurement of voltage. Okay. So now let's come to voltmeter, keeping this preliminary discussion in mind. Okay. Now voltage measurement with a timer. With a timer or counter, whatever you call. Okay. So what we shall do? We first need a balance like this, which can, here this balance can compare two weights, which one is heavier. Similarly, we need a instrument which can compare two voltages. Okay. So we need a voltage comparator. Okay. This is one thing that we need. What else? Definitely we need this counter or timer like this stopwatch, a counter or timer. What else? Something equivalent to this tap. And what would be the equivalent of this tap? So we will need something that will increase our voltage gradually and uniformly. Like this tap was increasing the weight of this beaker gradually and uniformly with time. Similarly, we need something that will generate a smoothly increasing voltage, uniformly linearly increasing voltage, and that is called a ramp generator. Okay. So these are the three things we need: this balance equivalent to this comparator, the counter we need, and equivalent to this tap we need a ramp generator. Okay. So let's see them one by one. Number one, comparator. What is a comparator? We have already seen it. We can use simply a op amp. Okay. So a op amp, we know this acts as a comparator. Simply if we just connect two voltages V1 and V2 at two terminals, say plus and minus, okay, then the output we know, this tells us which voltage is higher. Okay. So this is positive if this V1 is higher, V1 greater than V2, and this is equal to negative if V1 less than V2. Okay. So this is a comparator. Now a ramp generator, I will just draw the block diagram now. Okay. So this will give a output where the voltage will increase like this with time. If this is time, this is voltage or output. Okay, this is a ramp generator. And third thing, timer. Okay, timer I don't have to say anything. Now, how do we put them together? So, to put them together, take the comparator plus minus. So, you have to compare two things. One is the unknown voltage. So, you connect the unknown voltage here, unknown voltage, which is the input also. Here, this one you connect this to the ramp generator. Okay. So, connect it like this. So, this voltage will increase with time like this, V versus T. This will increase like this. This output, now what will be this output? This input is initially higher than this input, this one, because initially this is 0. Assume the input to be positive. Okay, assume this to be positive. So, initially this is higher. So, the output will be initially high and then it will become low. Okay. Initially the output will be positive and then as this is increasing, then at some moment this value will become more than this value, then the output will go down. Okay. Now, this I will use, now what I will do? I will measure the time required for this output to go from positive to negative, which means the time required for this ramp to cross the input. Okay. So, call this input and and this is the ramp. Okay. So, let me draw the timing diagram as well. Let me do it on the same axis. So, this is time, input is constant, input has to be kept constant. Say the input is this is input, this is input voltage. Okay. And the ramp voltage is initially 0 and then it is increasing slowly linearly like this. So, this is the ramp, this is the input. Now, this is the time required for the ramp to go higher than the input, cross the input. Okay. Now, if this time is equal to, say, call it T1, and if the slope of this ramp is, say, what can I say, V volt per second, voltage per unit time. So, this is how fast the ramp increases. Okay. So, this value increases at a rate of V volt per second and this is T1 second. Okay. Then what can we say about the input voltage? If I know this time T1 and this rate, okay, then I can say that the input voltage is same as T1 second multiplied by V volt per second, same as V T1 volt, right. So, this was the unknown T1 and this V, these two are known. T1 is measured So, this is measured, this is known, we know how fast the ramp increases, and this was the unknown. So, we can find the unknown by this two measured and known quantities. Okay. So, okay. Now, so what we have to do? Essentially, we have to measure this time required for the input to cross the required for the ramp to cross the input. So, for that we will take a counter. Let this be a counter. Okay. It should have a reset input, of course, so that the counting starts from 0. We should not forget to reset the counter before the counting starts. Okay. And it should also have a clock, maybe positive edge triggered or negative edge triggered. Let this be the clock. And we have to drive this with some clock generator, square wave generator, okay, maybe some crystal oscillator or something. So, we need a clock generator. Okay. Let me put it here. And then what I will do, so I also have to make sure that the counter is stopped the moment the ramp crosses the input. Basically, the task of the counter is to measure this time. So, at this moment, so at this instant, counter will be reset. So, we have to start the counter from 0 value at this moment. So, reset and start at this moment, and then at this moment the counter should be stopped. Okay. Okay. And then the value of the counter at this moment will indicate the time from here to here. Okay. So, to make sure now that the counter is stopped at this moment, what I will do is simple, just like we did for we also did it for a frequency meter. We will take just a AND gate, and this AND gate gets one input from the clock generator. Okay. So, this is how this clock goes through the AND gate and drives and increments the counter. But here I will connect this. Okay. So, what happens here? So, let me just put a note. So, the moment this ramp increases beyond above input, when ramp becomes higher than input voltage, then this output, call it VO, then this output, then VO should will become negative, will become go down from positive to negative value. Now, assuming that this positive value means logic high, digital logic high, and negative value is same as the digital logic low, okay, or we may need some converter to for this to happen. Okay. But if this is so, then when the output goes to low or negative, then the counter will be stopped, because now this is low. So, AND gate will pass only 0. So, it will not pass this this clock. Okay. So, this clock will not pass through this AND gate anymore. Okay. So, the clock will stop because one input of the AND gate is low. Okay, so, the clock will stop at the moment when ramp becomes higher than the input. Okay. So, the clock will stop here automatically with this help of this AND gate. Okay. And therefore, the value of the counter at this moment will indicate the time that was required for the ramp to cross the input. Okay. Now, let us do a small math. Now, suppose we know the clock frequency is equal to f. Okay. If clock frequency is equal to f, and if counter value after the after this moment, okay, after the ramp crosses the input, okay, let me write counter value at the end is equal to, call it C for counter, then we can write T1 this time is how much? T1 will be counter value C multiplied by the time period of this wave. Okay. Because the counter value tells me how many clock cycles are counted. So, if I multiply this C with the time period of this clock, that will be this time T1. So, multiplied by time period, which is same as 1 over f. Okay. And from this, then we can write, now combining this is one equation and this is another equation. Okay. Now, combining these two, we can write the input voltage the same as V multiplied by T1, and T1 is C by F, right. So, this way we can measure the unknown voltage by comparing with a ramp voltage. Okay. Now, let us take some numerical examples. Okay. Okay. So, example. Suppose it is given that in a voltmeter like the one we talked before. By the way, this voltmeter has a name. Okay. This is called a ramp type voltmeter, linear ramp type voltmeter, linear ramp type voltmeter. This is the name we can give to this digital voltmeter. Okay. Now, okay. Suppose I tell you that, let us take first easy example, that in a voltmeter in a ramp type, linear ramp type voltmeter, the counter is driven by a say half megahertz clock, okay, and the value of the counter is say equal to 200 at the end of the measurement. Okay. And the ramp rate, ramp slope, say this is like say call it 5 millivolt per millisecond. Okay. So, these are some arbitrary numbers I am just putting. So, the question is input voltage is how much? Okay. Solution. Okay. You need not remember any formula. I always told you don't remember any formula, just understand what is happening. So, we see that the counter value is 200 and it is driven with a clock of 0.5 megahertz frequency. So, that means what was the time required for the ramp to cross the input. Okay. So, the time elapsed during the measurement is same as 200 and multiplied by or divided by 0.5 megahertz. Okay. So, this will become, you can calculate it yourself, this will be how much? 200 by half is 400 and megahertz means it will become a microsecond, right. Check my calculation, I may do some small mistakes. And so, this is the time elapsed, call it T1. Therefore, what is the value of the input? It will be same as the value of the ramp after this much time. So, the input will be same as this 400 microsecond multiplied by the rate at which ramp increases. So, time multiplied by rate of increase of the ramp, which is same as millivolt per millisecond. Okay. So, this is actually, so this milli you can ignore. So, then this is 400 into 5 means 2000 micro second goes away 2000 microvolt. So, it is same as 2 millivolt. Okay. So, this is the answer, right. Now, let us take another example or part 2, okay. Part 2 of this question. Say the so the nominal ramp rate, okay, this is this 5 millivolt per second or 5 volt per second, okay. 5 millivolt per 5 per millisecond is same as 5 volt per second, but actual ramp rate is 5 volt per second plus 1%, say 5 What do I mean by this? I mean that it is written on the ramp generator that the slope of it is 5 millivolt per second. It is written. That's what I think. Okay, but actually, due to manufacturing error or due to aging or whatever, the ramp rate is actually changed. It is changed to this value, 5 volt per second. 5 volt per second plus 1%. Okay, which is same as 5 multiplied by 1.01 volt per second. Okay. So, this is the actual value. Now, if this is the case, the question is how much will be the error? Okay. So, we will have error. Why? Because the nameplate rating or the nominal rate value of this ramp is 5 volt per second. Okay. So, nominal ramp value, ramp rate is 5 volt per second, but actual value is how much? This is 5.05 volt per second. Okay. So, if I believe in this value, then we will estimate the unknown voltage as, so estimated input will be how much? So, just let us use this from this. So, it will become 400 microsecond, 400 microsecond multiplied by 5 volt per second. So, this is same as 2 millivolt per, as we computed before. So, this is what we will believe the input to be. We will think the input is this much, but actually input is how much? Actual input, this will be this multiplied by 5.05 volt per second. So, you can calculate how much this is. So, this will be I think 2.02 okay, millivolt. Sorry, yeah, 2.0 millivolt. So, please check my calculation. I do not have a calculator with me now. So, if I do any mistake, please forgive me and tell me in the forum. But you can do this multiplication. So, then how much is the error? Then error is nothing but say the percentage error. We can compute this as this is the error 0.02. Okay. So, this will be 0.02 millivolt out of 2 millivolt. So, this is I think 1%. Okay. You multiply this with 100, this will come out to be 1%. Now, let us take part 3. Now, part 3. Okay. Now, assume that the ramp rate is perfect and it is perfectly 5 volt per second in the previous example. Okay. So, the ramp rate is exactly what is written in the specification. Okay. No error at all. But the clock generator or the crystal is slightly erroneous. Is erroneous. Okay. Such that the nominal frequency, how much it was? Nominal frequency 0.5 megahertz. Okay, 0.5 megahertz, but actual frequency, so this is, let me take this is 0.5 plus 1% megahertz. So this is 0.5 multiplied by 1.01 megahertz. Okay. So if this is the case, then how much will be the error? So let us compare. So nominal frequency is 0.5 megahertz and actual is 0.5 into 1.01 megahertz. Okay. Now estimated input. How much is the estimated input? So okay, we know the estimated input is definitely like this. Okay, ramp rate multiplied by the counter value divided by the frequency. Okay, so ramp rate is 5 volt per second multiplied by the counter value. Counter value is how much? It's given here, 200 divided by the frequency of the clock, which is if we use the nominal value, given value, this is 0.5 megahertz, and this will come out to be 2 millivolt. But the actual input is how much? This will be 5 volt per second multiplied by 200, and here I have to put the actual frequency of the clock, which is okay. If you calculate this value, this will be of course less than 2 millivolt, because we have this factor. So this will be 2 millivolt divided by 1.01. It is less than 2 millivolt. Okay. So now how much is the error? I do not have a calculator, but I guess if you do this division 2 millivolt by 1.01, this may come out something like 1.98 millivolt. Please check. Okay, I do not have a calculator, please check it yourself. So the error, percentage error will be how much? So this is like, so the difference between these two is once again 0.02, or actually you can write a minus 0.02 if you want, or let us forget about the sign, divided by 2 millivolt by millivolt. Okay. So this is once again 1%. Okay. So you have a error. Now the essential point which I wanted to convey through these examples, this is also this was also examples for our practice, but also there is a message. There is a message. The message is that if either the ramp rate or the clock frequency are not perfectly consistent with each other, or not perfect, clock frequency are not perfect, but are right perfectly consistent, with each other, then we will have error. In measurement. Okay. So, this is a problem with this is very important. So, I highlight it with many color. Okay, I also use highlighters. So, this is very important. Okay. So, and that is why we shall see other schemes, other modifications of schemes where this problem will be gone. Okay. So, this is one point you must bear in your mind, that if either the frequency of the clock is deviating from the nominal frequency, or if the ramp rate changes due to manufacturing error, aging, whatever environmental factors, then this meter will not give perfect result. Okay. Thank you. Let us meet again with more sophisticated instruments where this problem will not be there. Thank you.